Okay, so we said we were going to review today, so there's the review. Almost the whole course. One more thing we could add. The fundamental assumption of statistical mechanics. So every microstate corresponding to a given macro state is equally probable. So there it all is. That's what we've done this semester. Of course, there's some details in filling out the equations or deciding which principle to use when. So, but that's it. I thought what we'd do today is talk about a couple situations that allow us to review quite a bit of what we've done and bring it together in a slightly different perspective. And there are two things. The first is to talk about angular momentum quantization. Because it lets us talk about circular motion at constant speed and the momentum principle and angular momentum and electronic energy levels and the size of atoms and things like that. And then I thought we'd talk about a problem involving torque and momentum and angular momentum and energy and rotational energy and all that good stuff too. So, angular momentum quantization, topic number one. So when Bohr made his model of the hydrogen atom, which, as you recall, boy, these are all things you better know if you need to write them down. Remember that the idea was that he made the simplest possible model, which is just good science. When you're starting out, don't make your models any more complicated than you need to. So he said, that's a pretty bad circle, isn't it? I bet Bohr could draw better circles. He said, let's think about the atom as if it's just like a planet orbiting a star. So let's say in a hydrogen atom, there's a proton, there's an electron, and maybe the electron is just orbiting the proton the same way that the Earth orbits the sun. So this is a problem, and he said, well, it's going to move in a circle. So the orbit is circular, and it's constant speed. And his basic idea was that maybe the amount of angular momentum the electron could have could only come in integer multiples of one number. And that number is h bar. So let's think about this situation for a minute. We're going to analyze it using the electron as the system. Which makes the surroundings be the proton, or more generally the nucleus. And so we're going to consider the system at some particular instant, let's say when the electron is up here like that. And let's say that at this instant the momentum of the electron is that way. Okay, so question number one is, what's the direction of dp dt, the rate of change of the momentum of the electron at this instant. And here are the possible answers. A, B, C, D, and E. This quantity is 0. So this is the question. What's the direction of the rate of change of momentum of the electron at this instant? The answers are A, B, C, D, 0. Okay, well, most people say 3 or C, and that's correct. That's the direction of dp dt. Let's make it green. And what are some of the ways you could think about this that would have allowed you to get this direction right? What's one way you thought about it? Draw two momenta, an instant before and an instant afterwards. So we could have P initial, and at this location, P final. At that location, well, almost. And so delta P is down, so dp dt must be down. What else could you have thought about? Okay, so the speed isn't changing, so there's no component of dp dt parallel to P. That's also good. Well, we're going to think about force in a minute, but right now we just want to look at momentum. What about the kissing circle? Points to the center of the kissing circle. What's the kissing circle in this case? The whole orbit, right? Because it's a circle, the orbit's a circle. So dp dt points toward the center of. So there are a variety of ways you could think about it. So good. So now the next question is, what is the direction of the net force acting on the electron at that instant? Okay, good. Also, so what are some of the, how did you think about the net force? How did you decide it was down? dp dt is indeed equal to F net, so if we get a net force that isn't down, one of those two quantities is wrong. How else did you think about it? This is the thing causing the force, isn't it? And so this is electrically charged, it's positive. That's electrically charged, it's negative. Positive and negative attract. So two ways of thinking about it, they both give you the same answer. That's good. So, in fact, F net better be really equal to dp dt. Okay, so circular motion, constant speed. We know a lot about circular motion at constant speed. So did Bohr, of course. So now we want to elaborate this a little bit. Because what we want to do is find out what we want to do is reason through to the answers to the following questions. If we assume that the angular momentum, by which we mean in this case the orbital angular momentum, the translational angular momentum of the electron, can only have certain values, it's quantized, how do we get to this thing that we said came from Bohr's description of the atom, which is, you calculate the possible values of kinetic plus potential energy, and it comes out to minus 13.6 electron volts over n squared. So want to know where these possible values of energy came from. And we know that that's also associated with particular values of the radius of the orbit. So where did that come from? So how did we get K plus U is negative 13.6 electron volts over n squared, and allowed radii of the orbits? And these two things better make sense in terms of the size of atoms and what we know about atoms here. So those are the two things we're trying to answer. And we're actually just going to do this very standard thing that we do, which is start with the momentum principle and work through it. So we have, why are we using the form of the momentum principle that says dp dt equals F net? Why not P final equals P initial plus F net delta T? We're looking at one instant, aren't we? So we're going to say dp dt equals F net for the system of the electron. And as somebody pointed out, because it's not speeding up or slowing down, we know that there's no component of dp dt that's parallel to the momentum. It must be perpendicular. And there's also no component of force that's parallel to the momentum, so we can really just focus on dp dt perpendicular is equal to F net perpendicular, because dp dt parallel was 0. Okay, so now we know that. We've already taken care of the directions. We know about both directions here, so for a little while we can work with magnitudes to make our lives simpler. So we're going to take magnitudes here. And what do we know about the perpendicular component this side of the equation, dp dt perpendicular? Yeah, it's this PV over R thing, or mv squared, so it's equal to the magnitude of P times the magnitude of V over the radius of the orbit, or mv squared over R if gamma is approximately equal to 1. And in this case, you might really wonder if gamma's going to end up being close to 1. But in fact, in this model, the electron is actually not moving at super high speeds. It's okay. So we're assuming gamma is nearly 1. And now we're interested in the other side of this equation. So let's fill it out. So here's the question. Which of these equations correctly fills out the right-hand side of this? We've got the mv squared over r on one side. In fact, it makes sense to write m sub e because that's the mass of the electron. All of these expressions should be kind of familiar, and you might be thinking about how you decide what to put here. Ooh. So 1, 2, and 5. Well, okay, so you just said that you knew the net force was pointing that way because the object in the surroundings that was causing the electron to go around in the orbit in the first place was the nucleus, right? So it's not a gravitational force, right? Electric. Okay, now, so what goes into the equation? We don't have to. Didn't have to memorize it, but what's involved in the equation for electric force? What? Okay, so there's a constant. There's definitely a 1 over 4 pi epsilon 0. What else? Well, okay, so here's the thing. It's an electric interaction. So we're talking about these charged objects. So the charge needs to show up in the equation, right? So even if you don't remember the equation, which you'll find on an equation sheet, you need to think about what's going on. Does the mass matter? So if this was actually not hydrogen, but it was deuterium, and there was a neutron in here as well as the proton, would that change the force any? It wouldn't, would it? Because the neutron's not charged. So we better have some charges. And so we better have the charge of the electron, which is a minus E, and the charge of the proton, which is a plus E. And then the question is, what goes in the numerator, in the denominator? Does the force fall off like 1 over r, 1 over r squared? It's a 1 over r squared force, isn't it? So there better be an r squared. And then we're taking magnitudes here. So we're getting rid of the negative sign. So it looks like we better have a 1 over 4 pi epsilon 0 E squared, because we took a magnitude over r squared. Yes? Okay. It's the latter. It's so small that it doesn't matter. And I think we even worked this out once a long time ago, and there were many orders of magnitude difference. It's an interesting, yeah, thousands, yeah. So there is a gravitational interaction. It's not wrong to think about it. It would be in the same direction, but it turns out to be so much smaller because the electric force is so strong that it's just negligible. And even if this thing is near the Earth, the force the Earth exerts on the electron is still very, very much smaller than the force that the proton does. So it turns out to be negligible. Okay. So we have this equation derived from the momentum principle. And so here's what Bohr's assumption was, and we'll see how we can work this into our equation here. He hypothesized that the translational or orbital angular momentum of the electron around the center of the atom, the absolute value, the magnitude, would be some integer times h bar, where remember h bar is 1.05 times 10 to the minus 34 joule seconds. It's Planck's constant over 2 pi. And so this is translational or orbital angular momentum. So it could have a value of 1 times h bar, or it could have a value of 2 times h bar, or 3 times h bar, but not 1.5. That's what Bohr said. So we need to fit this, we need to combine that idea with this equation, which is our standard equation for circular motion at constant speed. And in order to do this, we need to think about how we would calculate the translational orbital angular momentum of the electron at this point. So if we said, how do you find the translational angular momentum of this electron, what would we do? Well, we'd think about the definition of angular momentum, wouldn't we? So for translational angular momentum, what do we need here? Well, what are the things that go into it? Okay, even if we don't know exactly what the equation. Does it depend on momentum? Definitely better have some momentum in there, hadn't it? So we've got a momentum here. And it's going around this, so something about the fact that it's going around this point, so the R vector, isn't it? So here's an R vector. It happens to be R sub A cross P. So here's this, now we're running out of colors, orange. Here's the vector r, goes from the location of, we wrote C for the center, so we better say it's center. That's location C. So that would be how we'd calculate the orbital angular, translational angular momentum of the electron. And so the magnitude, of course, would just be the magnitude of that, which would be the magnitude of r times the magnitude of p times the, it's got an angle, what function? Sine of the angle. And in this case, since we're talking about circular motion at constant speed, what is this angle? 90 degrees. Okay, so sine of 90 degrees. So it looks like what we're going to end up with here is that the magnitude of r times the magnitude of the momentum is going to be equal to some integer n times h bar. Okay, so that means that if we say this is equal to r mv equals some integer times h bar, then the speed of the electron v is going to be nh bar over r times m. So we'll just plug this in here. So we're going to say that we're going to take mv squared over r here and just plug in this expression for v, which we get by saying, well, this is angular momentum is going to have only these values. So what we're going to get is, and I don't want to make any mistakes here, we get mass of the electron divided by r times that quantity squared. So we have nh bar divided by r times the mass of the electron squared is 1 over 4 pi epsilon 0 e squared over r squared. So this looks like it could use some simplifying. And so we'll crank away on algebra for a while to simplify it, because there seem to be lots of r's floating around and lots of m's and whatnot. And what we want to know, one of the things we wanted to know is allowed radii. So one of the things we'd like to do is just solve for r, see what radii are permitted here. So let's solve this thing for r, and when we get all done with this, we find that r comes out to n squared h bar squared over 1 over 4 pi epsilon 0 times e squared times the mass of the electron. Okay? So let's see what that comes out to be. Approximately, roughly, what order of magnitude are we expecting here for this? It's clearly not 10 kilometers, right? What are we kind of expecting here? Okay, knowing the size of an atom is a good thing, because it does come up. 10 to the negative 9th. This is actually a number you should just know. It's just a useful number. Okay. So it's actually, it's not a constant. This is approximately what's the size of an atom. If someone says, I have an atom here, what's its radius? Or someone says, calculate the diameter of an atom or the length of an interatomic bond, and you get an answer that's 10 to the 23rd. So what's the answer? So actually, I mean, what you can do is just do the calculation, which doesn't take very long. And you can leave the n squared in there because there are multiple allowed radii, of course. So if n is 1, you get one value, but if it's in the second state, you should get a different value. So just leave n in there, and then. So what does it come out to? Well, the biggest vote is for 4, and that's correct. Actually, it does come out to, we'll write it this way, 0.53 times 10 to the minus 10 meters. And really, if you're going to want to memorize anything that's going to be useful to you on the final, memorize the fact that the radius of an atom is about 10 to the minus 10th meters. Okay, knowing that number, approximately, I mean, this is 0.5. The first orbit of a hydrogen atom, we get 0.5 times 10 to the minus 10th. So the hydrogen atom is clearly the smallest possible atom. The other atoms are somewhat bigger. So on the order of 10 to the minus 10th meters, you should expect something like that. Well, that's what? Do they get as big as 10 times 10 to the minus 10th meters? I don't think so. I think they're more on the order of 1 times 10 to the minus 10th meters, a single atom, yeah. So it looks like times n squared. So the possible radii would be 0.5 times 10 to the minus 10th meters, or that's times, or 4 times that, 2 times 10 to the minus 10th, or 9 times that. So that's where those came from. That's where the radii of those possible orbits in the Bohr atom came from in this calculation. Now, we want to calculate the possible energies, because that's what we came out with. So we want to figure out how we got these possible values for energy. And so we'll write down here that R is 0.53 times 10 to the minus 10th times n squared. So what were these energies that we drew in this energy level diagram? What does the energy level diagram for the hydrogen atom look like anyway? So what does the potential energy function look like? So if this is separation and this is energy, what's the potential energy? Does this system have potential energy? Proton plus electron, it does. What kind? Electric potential energy, yay. What do I draw for the, what is the electric potential energy? It's negative. And as they get farther away, what happens to the function? Goes to 0. And as they get closer, it gets more negative. All right. So kind of looks like that. And in fact, this is the electric potential energy, which you don't necessarily have to remember exactly, but it's 1 over 4 pi epsilon 0 Q1 Q2 over R. Goes like 1 over R. And then we talked about these values. So there was one thing down here at the ground state was here, and there was a first excited state. And what is this quantity we're considering when we draw a line here? K plus U. So this is K plus U. So what we want to do is calculate the possible values of K plus U, and they better come out to be negative. And we're just going to make the assumption that this, again, we're going to continue to assume that this thing is traveling at speed small compared to the speed of light. So therefore, we're going to write k plus u. So what do I use for k? 1/2 mv squared. Mass of the electron v squared. And for u, yeah, potential energy, but I just put a q1, q2 here. So you have to be a little careful. So there's a 1 over 4 pi epsilon 0. There's a 1 over r. And what do I write for the charges? What's the charge of the electron? Negative e. And the charge of the proton is positive e. So this term is negative. We can rewrite it as a half mass of the electron v squared minus 1 over 4 pi epsilon 0 e squared over r. However, way back when we first started this analysis, we decided that from the force analysis we had dp dt equals F net, and so we had mv squared over r was equal to 1 over 4 pi epsilon 0 e squared over r. So we can just rewrite this stuff. And when we plug that in and solve, so, yes, sorry, r squared. So actually we can just solve for mv squared, and that's equal to 1 over 4 pi epsilon 0 e squared over, in this case, r. So we can plug that in, and so we get a half times 1 over 4 pi epsilon 0 e squared over r minus 1 over 4 pi epsilon 0 e squared over r, which gives us a total of minus a half 1 over 4 pi epsilon 0 e squared over r. And now we're going to plug in all these this value for r that we got. And we're actually going to plug in the whole expression. So we got r was equal to n squared h bar squared divided by 1 over 4 pi epsilon 0 e squared mass of the electron, I think. Let's make sure we got that right. Yep. So we plug that in, do more algebra, and we find that this comes out. So we have a minus a half 1 over 4 pi epsilon 0 e squared over that whole thing. So n squared h bar squared 1 over 4 pi epsilon 0 e squared m. And we get minus a half 1 over 4 pi epsilon 0 e to the fourth mass of the electron to n squared h bar squared. And when we actually plug in the numbers here, what do you think it comes out to? Yeah, that's what it comes out to. So actually in joules, it comes out to negative 2.17 times 10 to the negative 18 joules divided by n squared, and you convert to electron volts, and it comes out to minus 13.6 electron volts over n squared. So he started with circular motion at constant speed, and dp dt equals F net. And he said it's an electric force. And he just did the stuff, the standard physics 205 stuff, except that he made this assumption that the angular momentum had to come in units of n times h bar. And he got those values, which actually matched the energies of photons emitted and absorbed by hydrogen atoms. So that was pretty exciting. Now we now know that a more sophisticated model that extends to multi-electron atoms involves orbits that aren't circles. In fact, they're three-dimensional. So some of the orbits are just electrons moving in spherical patterns. Some are these interesting things you've seen in chemistry, the p orbitals, so they're moving in 3D patterns that are kind of dumbbell shaped. But it's still true that angular momentum of these things, in fact, can have only values of integer multiples of h bar. Now, one thing Bohr didn't know about is that the electron has rotational angular momentum also. It's just like the Earth, so it can be spinning around its own axis as well as moving around the nucleus. And it turns out that electrons have rotational angular momentum, and positrons and muons and neutrinos and all the other leptons. And their rotational angular momentum turns out to come in quanta of a half h bar. And you've heard of spin up, spin down for electrons in chemistry. All that means is rotational angular momentum up or rotational angular momentum the other way. Up compared to what? Some magnetic field. So it's just, so in chemistry we call that spin angular momentum, or in quantum mechanics, and we call this kind, translation we're talking about, orbital angular momentum, all kind of referring to Bohr here. And protons, things that are made of quarks, also have rotational angular momentum because all the quarks have little individual rotational angular momentum. So a quark has plus or minus a half h bar, and since a proton has 3 quarks in it, any way you look at it, it's going to have to add up to a half. Usually 2 of them are opposed. It's very unusual to get a state where they're all pointing the same way. So what did we review? The momentum principle? Just about. Angular momentum, translational angular momentum, circular motion at constant speed, dp dt perpendicular, the electric force. What did we forget? Okay, so if we've got a collection of hydrogen atoms, and we put in twice that amount of energy, how's it going to be distributed? What's the most probable distribution? Yeah, okay. So it works there too. So a lot of it comes together, and at the end it's sort of easy to understand because it was just assumed. The only new thing was assuming that angular momentum could only have certain integer multiples of h bar as a value, and then we're just doing standard physics 205 stuff, and this mysterious number drops out.